We're now going to use hybridization theory to describe the bonding in C2H4, also known as ethene. Now, if I draw the Lewis structure for ethene, what we're going to find is that there's a double bond between the two carbons, and that each carbon is bonded to two hydrogen atoms like this. Now, if I was to look at the steric number of each carbon, I'd see that each carbon is attached to, let's see, this carbon is attached to 1, 2, 3 other atoms, and there's no lone pairs. The steric number is 3. This is going to tell me that the molecule is going to be sp2 hybridized, in which a single s orbital and two p orbitals are going to mix, and those 3 orbitals are going to produce 3 sp2 hybrids. They're going to point to the corners of an equilateral triangle, such as what you see here. We want to remember that there are actually 3 p orbitals, and there's a third p orbital on the central carbon that is unhybridized. And we can envision this occurring in the following way. We're going to take our s orbital, and we're going to mix that with a py orbital, which is oriented along the y-axis. We're also going to mix that with an x orbital, px I should say orbital, which will be oriented along the x-axis. And when we hybridize these 3 orbitals in the xy plane, we're going to get these 3 lobes pointing at the corners of an equilateral triangle, lying in the xy plane as such. Now, this third p orbital, that actually sticks up and down out of the plane. We can imagine that like this, sticking up this way. If we just add the unhybridized p orbital, will be colored in black. Of course, the other side of that unhybridized p orbital would be sticking this way. And so we can sort of envision the unhybridized p orbital in black and the hybridized sp2 orbitals as the white pieces of foam. So that is going to be the picture that we have around this carbon atom. And of course, this is an identical carbon atom, and it's going to have the same sp2 hybridization as our first carbon. So let's just draw on this central carbon. We're going to draw an sp2 hybrid this way. We'll draw an sp2 hybrid this way, and we'll draw an sp2 hybrid this way. And then our second carbon would be here, and this would have an sp2 hybrid orbital here that would overlap with the other sp2 hybrid from our carbon here. And then we're going to have an sp2 hybrid here and an sp2 hybrid here. So each carbon atom has 3 sp2 hybrid orbitals. They're going to point to the corners of an equilateral triangle. And then we can just take the s orbital. I mean, that's what a hydrogen atom is, right? I mean, there's just one electron in a hydrogen atom, and we can envision that being in an s orbital that we're just going to overlap here like this. So this is sort of like just sticking hydrogen atoms on here. And the overlap between the s orbital on the hydrogen atom and the sp2 hybrid on this carbon atom forms the basis of the bonding between the carbon atom and the hydrogen atom in each particular case. Now, at this point, we've only described the bonding between the two carbon atoms, only one of the bonds, I should say, one of the 2 bonds. Where does the second bond come from? Well, the second bond actually comes from the overlap between the unhybridized p orbitals that are sitting up and below the plane of the paper, like this. I mean, if I rotate it, it's going to look like this. You see there's an overlap, if we can envision that, between the 2 carbon atoms, the unhybridized pz orbitals that are sticking up out of the plane of the paper. There's an overlap there. And of course, it's also happening down below the plane of the paper as well. So if these were the 2 carbon atoms in this plane, the overlap is also going to occur below the plane. So if I were to take this structure here and rotate it like this so you can see it side on, what we need to envision is that, or imagine, is that we're going to take the molecule and rotate it like this. So you're looking straight down through this plane of the molecule. And if we were to do that, and we were to imagine the two unhybridized p orbitals like this, above and below, what happens is there becomes an overlap of these two orbitals, and that is what forms the second bond. So there's a side-on overlap that we're going to envision sort of happening like this. Those two carbon atoms get close to each other, and then the unhybridized p orbitals, the pz orbitals, in fact, that are represented by the white pieces of foam on this carbon atom and the black pieces of foam on this carbon atom, they overlap each other like this. So there's an overlap of these two orbitals that is going to form this second bond. So to recap, in ethene, we've got our carbon atoms, each of which have 3 sp2 hybrids. 2 of these sp2 hybrids overlap between the 2 carbon atoms, forming the first bond between this carbon atom and this carbon atom. We take the 1s orbitals from each hydrogen atom and overlap that onto the second 2 of each of the sp2 hybrids on each carbon atom, and that's going to form the bonds between the carbon and the hydrogen in both cases. This second bond that occurs, the second bond in the double bond, that's going to come from the overlap of the pz orbitals that were not involved in the hybridization process. The overlap of those two is going to form the second bond between the 2 carbon atoms. So we could envision that as, if we're just looking above the plane of the paper and not the orbitals below the plane, these orbitals would overlap in this manner, causing that second bond. Now, when we describe these different types of bonds, we give them one of 2 names. We either call them sigma bonds, or we call them pi bonds. And here's the way you tell the difference between a sigma bond and a pi bond. In a sigma bond, if we can take a line and draw a line between the 2 atoms shared in the bond, like between this carbon atom and this hydrogen atom, if the line between the 2 centers in the atoms punctures the overlap, so you can see here there's an overlap here. If the line between the 2 atoms punctures the overlap, then it's a sigma bond. So this bond here between this carbon and this hydrogen, that's going to be a sigma bond. All the bonds between carbon and hydrogen, those are all going to be sigma bonds. This first bond, the first bond between the carbon and the other carbon, if you look at that, that's going to puncture the bonds there. That first bond in the double bond is a sigma bond. But the second bond, we see, if we look at the overlap, so we imagine these 2 carbon atoms, that overlap there, if I were to rotate it in this direction, all right, we see that if I draw a line between the 2 carbon atoms, it does not puncture the overlap between the 2 carbon atoms. And anytime that happens, then you have a pi bond. So this double bond consists of 1 sigma bond and 1 pi bond. And that's always going to be the case in a double bond. The first of the bonds in the double bond is what we're going to call a sigma bond. And the second one is going to be a pi bond. And that's going to result, again, from the overlap of the 2 unhybridized p orbitals. They're going to exist both, that's going to exist above and below the plane of the molecule.